Hi everyone, in this video we're going to go through section 10.3, hypothesis tests for a population mean. All the remaining sections of this course we will be looking at different types of hypothesis tests. So it's going to be a matter of using the right formulas and referring to the right distribution as you follow these same steps over and over. So hopefully you get really good at the redundancy of the steps while learning the various techniques to kind of close out the remainder of the course. So because we're talking about means in this section, right, that means that we're going to be computing t-scores and using the t distribution. That's really important. That's the one, it's table 7, where we have to, or 8, where we have to use the degrees of freedom and go over to whatever is the area in the right tail. And I will have a screenshot of that just in case it's been a while since you've looked back at that table. But everything else is the same other than the formulas. And by that I mean the procedure. Everything else, the procedure. Write down the null and alternative, what type of test is it, left, right, or two-tailed. All of those steps are the same, just new, different, slightly different formulas, and the t-distribution. Here we see a big giant slide of information. This is the same as it was in the previous section. It's on page 450, 451 in your textbooks. Again, I'll highlight the key things to pay attention to here in terms of our steps. We write down our null and alternative hypothesis first. Then step 2, our level of significance alpha is going to be given to us. And then in step 2, remember, that's where I like to draw my distribution and find out what where my critical region is, what t-scores separate that critical region, okay? Then we're going to compute our test statistic. That is based on our sample data, right? That has the mean and the standard deviation of our sample data. So this is our x minus mu over sigma z-score formula, but specific to the context of this section. It's a t-score, x bar minus mu naught. Mu naught is from the null and alternative hypothesis, the hypothesized mean, and then s over radical n, standard deviation, and then the square root of our sample size. Okay, then we compare those two values. So step 4 is, do you reject or do you not reject the null hypothesis? Right, so there's step 4. And we base that on whether or not we fall into that critical region. Does the test statistic fall in the critical region or not? And then step 5 is write a fancy sentence, interpret it in the context of the problem. And we'll do that with the examples we look at today. And you will also be asked about p-value, especially on homework problems. Again, this is a purely Minitab question, this technology step 3. I keep doing that instead of highlighting. Technology step 3. Use Minitab to get the p-value. If the p-value is small, smaller than alpha, reject the null hypothesis. All right, now pause the video if you want to read through this example in its entirety, but we're talking about the heights of American males, and we're comparing the 44 U.S. presidents against the general population. So the 44 presidents have a mean of 70.81, a standard deviation of 2.75, whereas the general population is the 69.7 inches up there. And then the question says, to treat them as a simple random sample. They're not. They're a specific sample. But if we treat them as a simple random sample, is there evidence to suggest that the U.S. presidents are taller than the American male? And we're using the 0.05 level of significance. All right, now let's go through our step. Step 1, as it always has been, is the null and the alternative hypothesis. In the previous section, it was p equals. Now it's mu equals, and you can throw the little naught down there. If you leave that off, I won't mind. And then we're looking at 69.7 inches. That's what we're comparing our 44 presidents to, 69.7. And then because it says the word taller, our alternative hypothesis is that mu is greater than 69.7 inches. All right, there's step 1. Step 2, level of significance. Level of significance. There we go. Alpha is 0.05. So I'm going to draw my distribution. I'm going to label the right tail. And let's jump to red here. I'm going to label the right tail So that 5% of the distribution, alpha is 0.05, is to the right of some t-score, t sub alpha, and now I need to go to my table to find out what that is. Now, fortunately for us, I have our table down here. Now, one thing that we need to make a note of in going down here is our alpha was 0.05, and our sample size is 44. Go back in the video a few seconds if you don't remember why it's 44. But then n minus 1 for our degrees of freedom is 43, and we'll see in a moment where to find that. Okay, so going over to our t distribution, right? I'm going to go down the degrees of freedom until I see 43, and let's take a look. And when you get down to 40, oh, I got to scroll down some more. When you get down to 40, it starts counting by tens. Okay, so that becomes less, the exact number of degrees of freedom becomes less important the further you go down, because if you look here, there's very little change once you get past 30. Okay, so 40, 41, 42 doesn't really matter, but we're going to round that 43 to 40 and look right here at our degrees of freedom. Okay, but I've got to go back up because now I need to, I don't have to look up, I have it right here. And now I have my 0.05 for the level of significance, and then just look down and look across and see where those two meet. They meet right there at 1.684. That is my t-score that goes on my distribution up here, 1.684. That's the cutoff. Anything beyond that, reject. Anything less extreme than 1.684, don't reject. Okay, that's step 2. Now step 3 is where we compute our test statistic. So 3, test statistic. Okay, formula is t sub 0, t naught is equal to x bar minus mu over s over radical n. Now, where does all that come from? X bar, the sample size, or not the sample size, X bar, the sample mean is 70.81. That's the mean of our 44 presidents. And that doesn't, I didn't update this with the current president. He's really tall. He would bump the mean up a little bit. So this is just the previous 44 presidents. So sorry, I didn't, update it for some of the last 3 years. And then S, the standard deviation, we're given that is 2.75. What else do we need? N, our sample size, is 44. And then one other number in that formula, mu, is 69.7. That's from the null hypothesis. So we substitute in. Let me move my picture a little bit further away. We substitute in, and t is equal to 70.81 minus 69.7 divided by 2.75 over the square root of 44. If you like typing things all in one step, that's okay. The numerator needs its own parentheses, and you'd be wise to put a parentheses around the denominator as well. And if you type that in carefully and correctly, I got a t-score of, oops, I don't want to use red here, I want to use blue, a t-score of 2.68, or 677 if you go 3 decimal places. But the purpose is to come up here to our distribution and see where that 2.68 falls. And it falls somewhere to the right of 1.684. And so what does that mean? It means that we reject the, oops, I forgot a C there. Reject the null hypothesis. It has been rejected. No. Okay. And then our fancy sentence, step 5. There is sufficient evidence. There is sufficient, evidence at the 5% level of significance. Level of, I'm just going to abbreviate significance to conclude that the average heights of the presidents, 44 of them, are taller than the average American male. Okay, so there's a fancy sentence. A variation on that is okay. It doesn't have to be word for word, but if you're a memorizer, maybe you want to memorize that layout. There is sufficient evidence, 5% level of significance, and then you use the words from the problem. Okay, so what does that mean? It means that if you're short, don't run for president. It doesn't actually mean that, but it means that generally speaking, we like to vote for tall males, unfortunately, but that is what the past data shows, and maybe that'll change, hopefully sometime soon. Here we get to our next example. Pause the video if you want to read through it once. But we have a mean travel time in Texas, 27.3 minutes. Department of Transportation reprograms things. Sample 2,500 commuters, and their mean travel time after the reprogramming, 27 minutes. Standard deviation, 8.5 minutes. Does this suggest that travel time has decreased at the 5% level of significance? And I'm also going to underline the word decreased. So I'm picking out the key things there so that when we write down our work here, it's easier to find things. Our null hypothesis is that mu is equal to 27.3 minutes, and the alternative is mu is equal to, no, it's not equal to, is less than 27.3 minutes. Remember, those two numbers are always the same. The first equation is always an equals. The second one, you have to find that key word, and I underlined it in blue. Now, why did I pick 27.3 over the other number, 27? Right, that 27 minutes here, that refers to the sample of cars. That is X bar, the sample mean. That's how I knew that that was not going here. All right, step 2, level of significance. We'll abbreviate that. Alpha is 0.05 again. Alpha is 0.05, so I draw my distribution. Ooh, that was terrible. Try again. I draw my distribution. That came out decent. I'm going to put the t-score on the left. Let me make it red. Shade to the left of that. This is a left tail test, right? Over here is 5% of the distribution, but what t-score corresponds to that? It's a negative number because I'm on the left-hand side, but negative what? Well, we've got to find out by going down here. Okay, our alpha is 5%, and our sample size is huge in this one. Alpha is 0.05, n is 2,500. Huge. And if you look down at the bottom, you have 1,000 or z, right? So what does that mean? I mean, you could really use either one, and if you look, they're really, really, really close together or the same, right? Super duper close together or the same. Once you have a sample size that big, that it doesn't really matter. The t distribution, as your sample size gets bigger, approaches the same layout as the z distribution. That's kind of what happens here. Okay, so all I've got to do is go over to 0.05 right there, go down to the bottom of that column, and I could really pick either of those two numbers and get virtually the same results. I'm going to use 1.646, but it doesn't matter which one you use. Okay, so that's my t sub alpha, 1.646. And notice here, right, that table only has positive values, but I knew to make that a negative t-score. How did I know that? Because I'm on the left tail. Left tail has negative t-scores, right tail positive t-scores. All right, moving on to step 3, my test statistic. All right, for that I need the formula. T naught is equal to x bar minus mu naught over s over radical. Radical n. There we go. Substitute in everything that's given to me. X bar is the 27 minutes. Mu, 27.3. Sample size, huge. Oops, no, that's wrong. Standard deviation's up top. Sorry about that. 8.5 over the square root of the sample size is huge. There we go. That's much better. Okay, and again, if you're typing this all at once, I generally do the subtraction first as its own step and then divide with a parentheses. That's just the way that I like to do it. But, figure out what works best for you as long as you're getting it correct. And when I type this into my calculator, I got negative 1.764, negative 1.76. So we'll follow that over to our distribution, see where it falls. Is it beyond that t-score? Oh, it absolutely is. It's somewhere. Actually, it wouldn't be over that quite that far. Probably more like here. But it is beyond the cutoff. It's in the critical region. So step 4, we reject the null. Reject the null hypothesis. There is enough evidence to conclude that the average drive time has decreased following the reprogramming of these lights. Okay? But the question is, did the average drive time really decrease? Think about that. What was the old drive time? Excuse me. The old drive time, 27.3 minutes. The new drive time, 27 minutes. That's like 18 seconds difference. That's not a big deal. The reason that we can make it seem statistically significant is by taking this giant sample of 2,500, right? If that sample were only 25, feel free to run through things again with a smaller sample size. It wouldn't be statistically significant. Or if it were 30 or 40, it probably wouldn't be statistically significant. But because we use such a large sample, we can show significance in something that's only an 18-second difference. For those people driving to work for 27 minutes, 18 seconds off their drive isn't really going to matter. And that leads us to this kind of concluding thought to end the section, that large sample sizes can lead to results that are statistically significant, but not practically significant. Practically meaning like 18 seconds on my commute isn't a big deal. Right? Especially when my commute's 27 minutes. So that closes out the section. Get to work on some homework. If you have questions, please shoot them my way, and have a wonderful day. Thank you.